Hello, this is the Clean Ballast Water team. My name is Ariana Redondo.
I'm Martha Priestley.
And I'm Alex Williams.
Our client was Andy Priest from Integrity Pools located in Florida. Our faculty advisor was Dr. Ronald Lacey, and our project manager was Dr. Sivko Nikolov.
Okay, so our project involved the disinfection of water in ballast tanks. Ballast tanks are tanks in the bottom of ships that help with buoyancy and stabilization. When these ships arrive into ports around the world, they have to discharge this water that's stored in these tanks. When this happens, it spreads invasive species and other disease. Our client system will use ozone and sodium chloride to disinfect that water while it's stored in the ship's ballast tanks. These chemicals were chosen due to their bactericidal, algicidal, fungicidal, and clarifying properties. If you look on the image on the left, this is a diagram that shows what the system will look like once it's actually implemented. The image on the right is the system that we actually use for testing. As you see the tank on the right, water will flow from the tank through the pump into the top of the ozone column. It will exit the ozone column and return to the tank, and this will be repeated. These are some drawings of our client's patent. If you look on the left image, number 42, this is the ozone injection. This uses a Venturi injector, which creates a pressure differential, which will force ozone into the tank. When the ozone enters the top of the tank, the larger bubbles will tend to gravitate towards the top of the tank, where they'll eventually be broken down by the impact of the water. The finer the bubble, the lower the buoyancy of the bubbles, and therefore the greater the likelihood that they will be entrained in the downward and outward flowing water. So ultimately what's leaving the tank is a superfine bubble, or in some cases a completely dissolved ozone. Our client's technology in theory is more efficient than other ozone injectors due to the laminar stratification of these gas bubbles, meaning that the larger bubbles will remain on top of the tank until they're finally broken down. The smaller the bubble means the better the contact with particles in the water, which will mean better disinfection of the system. As water is recycled through the system, the ozone concentration will continue to increase its oxidative potential, which will increase the efficiency of the system. So for our project, we had 3 sample acquisition alternatives and 3 testing alternatives. The first sample alternative was to create our own water. This would have involved matching the salinity and elements found in ocean water. Many elements found in ocean water have reactions with oxidative chemicals, and without these, the experimental data would not have been representative. So this option was discarded. The second option would have been to collect samples from ships' ballast tanks that are coming into the Port of Houston. This would have been the most representative sample, but was unfeasible due to various constraints, such as having to get a permit to even enter the port, much less getting permission to collect some of that ballast water from these ships. So given the time constraints, this was discarded. The third option was what we decided to go forward with, which was to collect samples from the ocean and simulate the conditions alike to those in ballast tanks. This will be discussed a little bit more in the next slide. We had 3 testing alternatives. The first was various experiments to determine if samples would pass minimum discharge requirements. This would involve getting a plankton net, which would have filtered out organisms larger than 50 micrometers. Once these are filtered out, we would have enumerated them and made sure that the number in the system was less than allowed by the IMO, the International Maritime Organization. These limits are shown in the table. This was discarded due to the complexity and the time constraints of the project. The testing option number 2 was the BW700 ballast water validation kit. This is what operators use on ships to make sure that their discharge is meeting these requirements. This is a very expensive device, and not all of the parts of the device would have been applicable to our testing, so this was discarded. The last option, which is what we went forward with, was testing for ATP.
Within our final design, we had 3 design solutions which encompass sampling, treatment, and testing solutions. For our sampling solution, our client collected water at Trinity Bay to obtain a comparable salinity. With this water, we then seeded 2 out of 4 of our 35-gallon samples with organisms. The chosen organisms represented living things commonly found in ocean water. Testing these organisms show the range of disinfection ability of the system. For the water treatment solutions, we used ozone and ozone plus sodium chloride. These solutions were the water treatment solutions the client presented us with. For the water treatment testing solution, we conducted ATP testing before and after to determine percent disinfection. This testing solution allows for quantifiable readouts of free and total ATP. By subtracting free ATP from the total ATP, the number of organisms present in the water is measured.
For the grand total of the organisms, which was the bacteria, protozoa, and copepod, it was $130. The testing kit was $2,500 with a grand total of $2,630. While it was clear that disinfection took place, the amount of total suspended solids in the sample water was too high. Due to the amount of silt, sand, and heavy debris that was taken from the low tides in Trinity Bay, the samples had a large oxidation reduction potential demand that had to be overcome by the ozone. Since the ORP value of 650 millivolts was not reached, it is likely some chlorine was created in the system. Chlorine is a carcinogen that is prohibited for discharge by the IMO. Due to the difficulties and roadblocks from the COVID-19 pandemic, further acquisition and testing was not possible.
As was mentioned, since the water was taken during low tide, the amount of suspended solids in the sample was much higher than would have been seen in normal ballast water. For this reason, the ORP demand was too high and never reached the expected value. So for this reason, we recommend if further testing is to go forward, it will need to be ensured that the TSS in the sample water is lower and matches what would be seen in normal ballast water. Another option is if the TSS is too high, to add a filter system into the system. This would allow the filter to catch a portion of the solids, allowing for the ozone in the system to perform more efficiently. Lastly, another option to increase the efficiency of the ozone would simply be to increase the injection rate. This would help the ozone overcome the ORP requirement.
We would like to extend our sincerest gratitude and appreciation to our client, Andy Press, and his colleagues, Brian and Bill, for giving us the opportunity to expand our knowledge in the ballast water treatment industry. We would also like to thank our faculty advisor, Dr. Ronald Lacey, and project manager, Dr. Zivko Nikolov, for helping us through this process and supporting us as we navigated this project.
Thanks, everyone.
Thank you for your time.